Hello friends, welcome back. In this video, we are going to study the MO energy level diagram for the CO molecule. CO means the carbon monoxide molecule. Now in this structure, we can see that there is a triple bond between the two atoms. Two atoms, that is the carbon and the oxygen atom. So let us study this. So we are having the carbon monoxide molecule. This carbon monoxide is a heteronuclear diatomic molecule. That means it is formed by the two different atoms, and the two different atoms are the carbon atom and the oxygen atom. So we are having the carbon atom and the oxygen atom. Now out of these two atoms, one atom is more electronegative and the another atom is the less electronegative. So we are having the carbon atom. This carbon atom is the less electronegative atom, whereas the second atom, that is the oxygen atom, is more electronegative atoms. Again, we know that the atomic orbitals of the more electronegative atom contribute more to the formation of the bonding molecular orbital. Hence, we can say that the atomic orbitals of the oxygen atoms contribute more to the formation of the bonding molecular orbital and the less to the formation of the anti-bonding molecular orbital. Similarly, the atomic orbitals of the less electronegative atoms contribute more to the formation of the anti-bonding molecular orbitals and less to the formation of the bonding molecular orbitals. Hence, we can say that the atomic orbitals of the carbon atom contribute more to the formation of the anti-bonding molecular orbitals and less to the formation of the bonding molecular orbitals. Okay. So, let's see further. We are having the carbon monoxide molecule. So as it is a heteronuclear diatomic molecule, it is formed by the two atoms. And the two atoms are, the first one is the carbon atom. Carbon atom means it is having the atomic number 6. So as it is having the atomic number 6, its electronic configuration is 1s2, 2s2, 2p2. Right? Then the second atom is the oxygen atom. Oxygen atom with the atomic number 8. That means its electronic configuration is 1s2, 2s2, 2p4. So these are the two atoms, two heteroatoms, carbon and the oxygen atoms. And here you can say that the 1s2 atomic orbitals, 1s2 atomic orbitals of both carbon and the oxygen atoms. These 1s2 atomic orbitals, they are lower in energy. As they are lower in energy, they are not used for bonding, and hence we can say they are the non-bonding atomic orbital, right? And as they are non-bonding atomic orbitals, while writing the MO electron configuration, we have to write the letter K. Why letter K? Because these 1s atomic orbitals, the electrons, they are present in the first shell, and the first shell is known as the K shell. Now as there are two atomic orbitals, we have to repeat the letter K while writing the MO electron configuration. Okay. Then for the bonding purpose, we are having the 2s and the 2p of carbon and the 2s and 2p of the oxygen. So let's see further. The CO molecule is isoelectronic with the N2 molecule. That means the number of electrons present in the carbon monoxide molecule and the nitrogen molecule both are same. Hence we can say that the MO energy level diagram for the nitrogen molecule is similar to that of the carbon monoxide molecule. Only exception is that the energy levels of more electronegative atom, that means the oxygen atoms, are lower, that means nearer to the BMO than the carbon atom, right? So let's see the MO energy level diagram for the carbon monoxide molecule. So we know that we have to draw the MO energy level diagram across an axis, that is the energy axis. Then this is the outline of the MO energy level diagram, which is just similar to the nitrogen molecule, only we have to just shift the positions of the orbitals. Again, we know that at one side we are having atomic orbital, at the another side also we are having the atomic orbitals. Then at the center we are having the molecular orbitals. So the first atomic orbital is for the carbon atom, and they are 2s atomic orbital and 2p atomic orbital. Whereas the second atomic orbital is for the oxygen atom. Again it is 2s and the 2p. Now here we can see that the positions of atomic orbitals of the oxygen are lower in position. That means it is just nearer to the bonding molecular orbitals. Why? Because oxygen is more electronegative than the carbon. That's why its energy levels are lower than that of the carbon. And hence we can say that the oxygen contribute more to the bonding MO and the carbon contribute more to the antibonding MO. Then further we can say that the molecular orbitals, they are for the carbon monoxide molecules. So let us see their symbols. At the lower side, we are having the sigma 2s, that is the bonding molecular orbital, and the sigma asterisk 2s, that is the antibonding molecular orbital. And these are due to the overlapping or the combination of the 2s atomic orbitals of carbon and the oxygen. Then further we are having the 2p atomic orbital for the carbon and the oxygen. Again they are total 3 plus 3, 6 in number. Out of these 6 we are having the total 6 molecular orbitals. The 3 will be lower, that is bonding, and 3 will be upper, that will be the anti-bonding. So the bonding are pi 2py and the pi 2pz. They are degenerate because they are having the same energy. Then we are having the next bonding, that is the sigma 2px. Further, the second pair of degeneracy, pi asterisk 2py and the pi asterisk 2pz. And lastly, we are having the sigma asterisk 2px. So this is the MO energy level diagram for the CO molecule. Now let's see the filling of electrons. So how the electrons are filled in the MO energy level diagram. So first of all, we are having the 2s of carbon. The 2s of carbon, it is having 2 electrons. So this is the first electron and the second electron. Again, the 2s of oxygen, again having it is 2 electrons, the first one and the second one. So total we are having 2 plus 2, 4 electrons in the 2s. So these 4 electrons, they first of all filled in the bonding and then into the anti-bonding. So we are having the first electron from the carbon and then oxygen, again from carbon and the oxygen. So it is completely filled. The sigma 2s and the sigma asterisk 2s, they are filled by the electrons. Then let's move to the 2p of carbon. 2p of carbon consists of first and second, 2 unpaired electrons. They are filled by using the Hund's rule of maximum multiplicity. Then the 2p of oxygen, it consists of first, second, third and the fourth. The first 3 electrons are filled and then the fourth electron will be a paired electron. So we are having total 4 plus 2, 6 electrons. So these 6 electrons, they are filled in the MOs by using the Hund's rule of maximum multiplicity. So we are having the first electron in the pi 2py, then pi 2pz. Then they will be paired, the third electron and the fourth electron. The remaining 2, they are moving into the sigma 2px, first electron and the second electron. So in this way, there is a filling of the 6 electrons in the bonding molecular orbitals only. So this is the MO energy level diagram for the CO molecule. Now from this diagram, we can find out the electronic configuration. So for the electronic configuration, first of all, we have to write the letter KK for the 1s atomic orbitals. Then there will be the sigma 2s, 2, sigma asterisk 2s2, then pi 2py2, pi 2pz2 and sigma 2px2. So let's see this. The MO electron configuration of the carbon monoxide molecule is KK, sigma 2s2, sigma asterisk 2s2, pi 2py2, pi 2pz2 and lastly sigma 2px2. From this, let us find out the bond order. Bond order is equals to 1/2 into number of electrons in BMO minus number of electrons in ABMO. So the bonding molecular orbitals are 2 plus 2 plus 2 plus 2, total 8, and anti-bonding are only 2. So this becomes equals to 1/2 into 8 minus 2 and this is equals to 3. So the bond order is 3, means it indicates there is a triple bond between the 2 atoms. The 2 atoms are the carbon and the oxygen. So let us see the structure of the carbon monoxide. So we can draw the structure of the carbon monoxide as there is a triple bond between the carbon and the oxygen. And as there is a triple bond between the 2 atoms, It consists of one sigma bond and two pi bonds, right? So this is the structure of the carbon monoxide molecule, which is having a triple bond with one sigma and the two pi bonds. Here we can say that this carbon monoxide molecule is a diamagnetic in nature. Why diamagnetic in nature? If we see the MO electron configuration, the last entering electrons, they are paired. And as the last entering electrons are paired, we can say that the CO molecule is diamagnetic in nature. Then the bond length in the carbon monoxide molecule is 1.128 Armstrong unit. And the bond energy is 225 kilocalorie per mole. And lastly, we can say that the polarity of the CO molecule is very low. Why the polarity is low? Because there are 8 electrons in the bonding molecular orbitals. So these 8 electrons in the bonding molecular orbital try to neutralize the greater nuclear charge on the oxygen core. That's why the polarity of the molecule is very low. So this is regarding the CO molecule. So based upon this, let us move to the next. That means we have to see the drawback of the MO theory. In this we can say that a general consideration is that means when a ion is formed from a molecule. So for the formation of the ion there should be removal of electron, and that electron will be removed from the last MO, right? So if the electron is removed from the bonding molecular orbital, then the bond order decreases and the bond length increases, right? Or we can say that if the electron is removed from antibonding molecular orbital, then the bond order increases and bond length decreases. Why this is? Because we know that the bond order and the bond length, they are inversely proportional. Okay, bond order is inversely proportional to the bond length. So let us study this by taking an example of the formation of the CO plus ion. So how this CO plus ion is formed? This CO plus ion is formed from the CO molecule by the removal of an electron. Okay, so we have to find out whether the electron is removed from bonding molecular orbital or it is removed from the anti-bonding molecular orbital. If it is removed from the bonding molecular orbital, bond order decreases, bond length increases. So we can say that when CO is ionized to CO plus, that means when CO plus ion is formed from the CO molecule, it is formed by removal of an electron. And here we can see from the energy level diagram that the electron is removed from sigma 2px, and that sigma 2px is the bonding molecular orbital. So as the electron is removed from the bonding molecular orbital, we can say that the bond order should decrease and bond length should increase. But in fact, the bond length in carbon monoxide is 1.128 Armstrong unit, and in case of the CO plus ion, it is 1.115 Armstrong. So we can say that there is a decrease in bond length, but our consideration is that the bond length should increase, right? So we can say that thus the bond length decreases when we expect it to increase, and this indicates that the electron must have been removed from an anti-bonding MO instead of the bonding MO, right? So this suggests that the order of MO energy levels for heteronuclear diatomic molecules differs from that of the simple homonuclear diatomic molecules. So let us see this by taking an MO energy level diagram of the CO molecule, right? So from this diagram we can say that the last entering electrons, they are present in the bonding, that is the sigma 2px, and we have to remove the electron from the bonding only because they are the last electrons. So the most likely explanation of the bond shortening when CO is changed to CO plus is that the sigma 2s and the sigma asterisk 2s MOs differ in energy more than as shown in figure. That means instead of removing the electron from bonding, the electron should be removed from the anti-bonding, and the anti-bonding electron is present in the sigma asterisk 2s. So we can say that the position of the sigma asterisk 2s should not be over here. It should be at the last. That means over here. This means that They are the sigma 2s and the sigma asterisk 2s. They are wider apart. And the sigma asterisk 2s is higher in energy. This sigma asterisk 2s is higher in energy than the sigma 2px, pi 2py and the pi 2pz. This suggests that the MO energy level diagram of the CO molecule is not fully correct. So this is regarding the MO energy level diagram of the CO molecule. This indicates that it is a heteronuclear molecule in which we have studied the formation of the CO plus ion, and this also explain the drawback of the MO theory. Thank you.